Good. Okay, I'd like to say a little bit about DNA. This is going to be my bit of DNA today, and that's the straight DNA. DNA, as you know, is the molecule that transmits the genetic information. A molecule of DNA is in every cell of the human body. This DNA, which is over there on the table, I'm going to go there in a minute, is magnified about 35 million times to get from DNA to what you see over there. DNA is actually a double helix. Unfortunately, this thing that I found in a local pet shop is a triple helix, but anyway, it's good enough for today. You see, if you go down there, you come back out there. Meanwhile, the blue, red, green, yellow should be thought of as the genetic code. The genetic code is a series of chemical messages lined up along one of the helices. The molecule is often drawn straight as there, but in fact it very often gets coiled up, and that's why I bought this at the local pet shop. Anybody know what this is? Yes, it is a parrot perch. A fellow said, "What sort of parrot have you got then?" And I said, "Well..." So this is a parrot perch. DNA gets coiled up like this. So this is the DNA helix, and the helix itself has become a helix, and this is called supercoiling because it's something on top of the helix that was already there. I was absolutely delighted when I saw this because it was just what I needed. To represent the DNA in one cell of your body, you would have to think of 2,000 miles of that. And then you'd have to think of that 2,000 miles scrunched up into the Millennium Dome. And that would show you the sort of state that DNA is in a human cell. There's an awful lot of it, and it's scrunched up. It's a pretty tight fit, shall we say. And DNA does get itself knotted. And it's very important that it shouldn't get knotted, and it actually has very ingenious ways of unknotting itself. If a knot gets in the DNA, it has ways of sort of cutting itself and releasing the knot. So there's some very sophisticated devices there. But in order to begin to understand how DNA might compact itself, one can go to very simple experimental tests. I want somebody to turn a handle. Would you like to turn a handle? Very easy. Are you all right? Come on then. You can turn the handle for me. Make this DNA twist up, okay? I just want you to turn that handle, okay? Right. Just keep going. Doesn't matter really. Just keep going. Okay. So this is just an elastic rod. Look, it's buckling in the middle. It's quite an interesting buckling process. It's actually a pitchfork bifurcation of the type we've been discussing. Keep going. Keep going. It's forming... Is it getting hard? No. Just keep going. It's forming a little ply, and the ply is bending over. Okay. Faster? Turn as fast as you can. So it's forming a sort of a helix like we had before. All right, thank you very much. I'll just finish it off now, okay? Lovely. Many thanks. Round of applause, please. Right, so I'll just keep going rather quickly. Forms this lovely little sort of helix. It's quite tricky to work out the mathematics of this. In fact, somebody's just published a paper on this in the States. So there it's formed a beautiful little helix, and if you keep going, the helix forms a helix. You notice it's happening on the left-hand side there. The helix is forming a helix. Well, it's happening at both ends, actually. I'm running out of energy on this. Okay, we'll leave it there. Good. So you see the helix has formed a helix, and you can keep on doing this, and you can learn something about how DNA sort of compacts. I thought, to be quite honest, by now it would have broken. It usually breaks. And there's a sort of example of these little experiments. One does learn quite a bit about DNA by doing mechanical tests on rubber rods and things like that. And in fact, DNA often forms a little loop. If DNA forms a loop, it's called a plasmid, and those loops are rather like this, and those plasmids do often flip into the S shape, and a lot of research has been done on that. DNA can't function properly if it gets itself too taffled up. So there's a thing called the topoisomerase that can come along and untaffle it. It's rather clever. Okay, I'm going to say a little bit about catastrophe theory now. Catastrophe theory was a sort of a branch of bifurcation theory, really. It's a mathematical theory that helps you understand how things become unstable. I've already mentioned that a typical rolling surface would just have minima and maxima, but if you vary one control, you can typically encounter this horizontal point of inflection. So catastrophe theory really turns the common sense ideas of typicality into a very precise mathematical theory with concepts such as, for example, structural stability and things like that. And it reinforces the fact that it's only really worth discussing things that are typical. Some aspects of mathematics are very much concerned with things that are non-typical. There are whole branches of mathematics devoted to non-typical events, but in dealing with instability problems, it's really rather sensible to concentrate on typical events. And as I mentioned before, a perfect column is not typical. You cannot encounter a perfect column. Okay. I said that you couldn't get to a pitchfork bifurcation. There is a way you can get to a pitchfork bifurcation. You put another load on. So if you have the top load here, if you put a side load on as well, and if you're prepared to systematically vary both of those loads, in other words, if you're prepared to systematically vary P and R, then you can get to the bifurcation. And this is an aspect of catastrophe theory proves this in a sort of rigorous sense. Suppose you put on a side load R, then a certain value of R, let's call it R star, is necessary to bring you back to exactly to the pitchfork. So if R is less than R star, for example, if R is 0, the column skates up here because I'm assuming it's got an initial bend to the left. If R is greater than R star, it goes to that side, but if R is just equal to R star just balances out the inherent imperfections in the column and brings you back to a bifurcation point. So an important feature of catastrophe theory was that it allowed you to say for each type of instability you had, how many control parameters you'd have to be varying in order to observe it. And so far we've seen that you only need to vary one control parameter to get a fold, but you need to vary 2 to get a pitchfork. Well, now we're going to talk about dogs. Christopher Zeeman, at the time that catastrophe theory was very popular, applied sort of the ideas of catastrophe theory to lots of sort of psychological soft science applications, and this is one that I always thought was rather convincing. We're going to imagine a dog is a black box. The dog is a black box, and perhaps there's a little you're not familiar with these little electrometers. There's a little dial which shows you how the dog is behaving. And we're going to imagine that we can control the dog's rage and his fear. So these are to be thought of as loads, if you like, control parameters. Now, Konrad Lorenz studied what a dog looks like. This is a normal-looking dog. When he's angry, he shows his teeth and his ears come forward. When he's frightened, his ears go back. But if he's got rage and fear, he looks like this, and that's a very dangerous dog. You should always avoid dogs looking like that, because he can't quite decide what to do. You know, he's sort of really nervy because he's angry and afraid. Okay, so the suggestion was that this is how the dog would behave. What we've got here in the yellow base plane, we've got rage and fear, so we can move about, we can vary our 2 controls on this black box. We can watch how the dog behaves, and if it's up high, he's attacking, and if it's down low, he's retreating. The idea then is that if the dog doesn't have very strong emotions, in other words, we're on the back here, he can change from avoiding you to rather neutral behavior to growling without anything very serious happening. But if we come up to the front here, in other words, if he's got very strong rage and very strong fear, then if he were retreating but he got crosser and crosser, he might come up this way and then would suddenly attack. In other words, there would be a jump. This is an equilibrium surface. It's not a thing that balls roll on, okay? And the red is stable and the green is unstable. So if you were gradually moving along here, he'd suddenly attack. And then if he became much more fearful, he wouldn't immediately cease to attack. He would then come to this point and suddenly retreat. And of course, the same thing happens in wars. In fact, this was used to try to model the Vietnam War, which I thought was stretching things a little bit. But it is clear that a nation will sort of suddenly declare war, and then if it gets into a fearful state, it doesn't immediately sort of surrender. You get this looping behavior. So, and this is a pitchfork bifurcation. In fact, this is a three-dimensional view of a pitchfork, and there's the pitchfork itself, just at that point there. Well, whether you find that convincing or not, I don't know. It struck me as being fairly useful, perhaps, way of thinking about dogs. Okay, so we're going to see a catastrophe machine now. Who's going to come and catch the catastrophe machine? I think we need somebody strong. You help me with the first one. Come on. I thought you looked like a good catastrophe machine catcher. Your job is to stand up there and catch it. Okay. The idea of the catastrophe machine is that we've drawn lines at right angles to the rim everywhere around the rim. So it's clear that if it's going to stand in this position, let's say, then the center of gravity must be on that line, the line that comes up from the normal to the rim. Okay? And I've drawn all the lines coming normal from the rim, and you'll find that around the outer edge there's just 2 lines, but in the center section there are 4 lines. So it means then that if the center of gravity is out here, there are 2 possible solutions, one stable, one unstable. And if the center of gravity is in the center section, there are 4 possible solutions, 2 stable and 2 unstable. So if I have a little device inside that can move the center of gravity, as it crosses this line, it really has to jump. This is actually a line of fold. So this line here, where the 4 region changes to a 2 region, is a line of folds. So what I'm going to do is I'm going to switch this motor on, and our friend over here is going to catch it. It's not going to leave the table, I don't think. I need my glasses. I hope you've got to be quick. Okay. Go on, get it! Okay, you weren't needed. Thank you. But it was good fun. So this little machine, oh dear me. Got to be careful with these things. They're like jumping beans, aren't they? And sort of motorized jumping beans. Basically, they've just got a big heavy weight inside that I can move the center of gravity in any direction.